And now we are extremely honored to welcome Charles Zhang, who is the keynote speaker. He's one of the best, in my opinion, like I said, the expert in static and dynamic analysis. He's the member of many program committees of A-class conferences all over the world. Charles, the microphone is yours.
Great, thank you, thank you. It's an overstatement. So my name is Charles, and I work in the computer science department at HKUST. And I want to talk about our experience in developing and deploying static analysis. So this is a joint work with my students and former students. So they are working industry, but still we're doing research, continue to do research together. So I guess the first question I want to answer is about this thing called Pinpoint. And it is a static analysis. Well, I guess anything related to code quality, I think static analysis plays a very key component. So Pinpoint is a static analysis platform developed by my group for finding bugs, right? So finding quality bugs or security-related bugs. It's a project that started around 7 years ago, and we saw great potential, and we tried to actually commercialize it in 2 years later. And 2 years later, it was acquired by Ant Group. That's the company behind Alipay. So somewhat it's successful. I think it's a successful piece of technology. At the same time, we have also made visible contributions to theory as well. So as Jäger mentioned earlier, we indeed managed to publish a lot of this technology of this platform in many top-tier software engineering and programming language papers, programming language venues. The technology itself, at least in China, was deployed in almost all Chinese, the big Chinese technology firms. And once upon a time, I'm not sure about it now, but the Chinese Google, the Baidu, the entire C++ is being was being scanned by Pinpoint every day. So about the former students, because they now work as Ant engineers, but we still collaborate to push this forward. So my talk will follow the usual academic rhetoric. I'll first talk about the kind of problems what lead to the development of Pinpoint, and also the goal of my research. Well, I think it's relevant to others as well. I want to talk about the code principles of doing static analysis at the enterprise scale. Okay, so I'll talk about what I mean by enterprise scale very soon. Then, of course, the motivation is past research is not adequate, and then we have a solution, which I have to say at the beginning that it is not perfect. It's far from perfect, but we are working towards this goal. So what motivated us for develop a Pinpoint is that we're making some observations, or we have some suffering from what I call the strange characteristics of modern software. So by the word strange, so I'm speaking from a academic point of view. So what I want to emphasize is that these are the characteristics are sort of downplayed by research, by reading research papers. You might disagree with me, but let's see what I mean. Okay, so what are the strange characteristics of modern static analysis? Is that a modern software enterprise scale software is that, first of all, the software that we're going to analyze is very big. Okay, very big. So I guess this is not a surprise, even in modern high-end vehicle cars, we have 100 million lines of code. Okay, so this is getting really, the size is getting really big. And even for IoT, right? So all these small devices, since we're able to pack silicon transistors in a small scale, even these small things have very large software running. I think the baseline is 1 million lines of code. Okay, so it's hard to find in real life a practical system, software system that's less than 1 million lines of code in that system. Okay, so that's the sort of the strange characteristic. That's the first one. The second one is not only these systems are big, they are also alive. Okay, so alive meaning that these systems are being updated in a very fast pace. So I have data until last year. So for example, for Linux, we have about 10 updates per hour over the year. Even for specialized software such as the Clan compiler, we have 4 updates per hour. For TensorFlow, the average update is twice an hour. Okay, so which means we have to complete. So ideally, we have to complete our analysis per update, right? So the goal is to ensure code quality. So for every update, so for every commit, we'll have to. It's time to check, right? So that's the sort of the frequency that we have to complete a cycle for static analysis. The cycle is pretty short. And the third strange characteristic is that we now have this supply chain problem, right? So I looked at the data in about 6 years ago, 2016. We already see that around 30% of the software are being purchased, so on average, are being purchased, not developed by anybody in the engineering team. Okay, and of course, for big companies like Huawei, we have in-house supply chains. We have different departments working on different components, and the source code is often not made available for many good reasons. And also the software today are evolving into this so-called cloud native, right? So for example, this is, I guess the trend is even more significant. That in 2020, we see Amazon Lambda deployment increased by 200%. And not only that, the average size of these applications, including dependencies, including the libraries they depend on, is only 25 megabytes. So remember what I talked about earlier, how big the software is. This means that for a complete system, at least from the static analysis point of view, the majority part of the system is dark, meaning that we have no source code. It's in the native format. Traditionally, we would have no way to reason about it. Okay, so this is also what I call strange characteristic. The fourth one is that, so when we do static analysis or we try to do static bug finding, of course we need a PDG, right? So that's a sort of fundamental data structure we need to start from, and then we do something else. But I'm going to argue that in modern software, it is getting very hard, if not impossible, to build a PDG. Okay, so there are two interesting development. The first is the the increasing use of what I call componentized deployment. Okay, so such as the serverless computing. So so that the philosophy is to partition the big monolithic functionality to many smaller components. Okay, and things like Lambda serverless computing relies on the infrastructure to manage the life cycle of the component, which means that from system level as a whole, the dependencies of the different components are actually built through callbacks. Right? So, so this is inversion of control. The second trend is the microservice. Right? So it's another trend for developing modern software is to cut up all these monolithic system into different services that live in different process space or even different nodes. Okay, so in other words, the data flow that you're interested in, the points to relationship that you want to reason about is actually across different process, even across different nodes on the cluster. Okay, so the dependencies are distributed. So putting them together, I'm arguing that our control flow is assembled. Right? So they're not really continuous. They are put together by different means. And this is not something that the traditional static analysis is used to handle. Okay, and the last characteristic is that for modern software, we not only need to test it by running them against the test cases, we also need to do source level testing. Okay, so for example, I guess many of us know that the British government have quality auditing of Huawei products, not on its performance or correctness, but on the source code. Okay, and in general, we have a lot of these source code level testing requirement, such as this avionics, such as the autonomous driving, right? The MISRA standards. Okay, so and also the companies have their own specific quality and cyber security requirements on the source code for many reasons. Okay, so we need to write test cases for the source code. All right, so what do all these mean to static analysis? All right, so I'm talking about enterprise scale. So in a way, I'm talking about being practical, right? So to have engineers really use your technology, there are a few necessary conditions, not sufficient, but necessary conditions. So of course, we have to do it fast, right? So as I said, big software systems are being updated every minute, every few minutes, so we have to do it fast. We have to do it fast, and we have to do it very frequently and fast, right? So the system is constantly being updated. We need to understand this opaque or dark code that we have. The most parts of your software system is being purchased or are belong to this platform that you have no control of, or you have no knowledge of. Okay, and also we have this non-local program dependency. We cannot reason program starting from the main function anymore. Right? So all these functions are being put together by callbacks or other IPC mechanisms. And we have to allow user to define source level test cases. Okay, so there's a component of customizing what code quality means in different settings, different companies, different sectors. So all of this are necessary because also from a practitioner point of view, because we actually went out to deploy them in industry. So this is what I observed, and then in other words, if we don't satisfy any of this point of these qualities, the customer would not buy our product. So that's why it's necessary but not sufficient. I mean, if you've done all of these, you probably still they don't buy, but for some other reasons. So based on this observation, I have a dream. Okay, so a dream means that I have not achieved it yet, but I think this is the right direction to go. So if we want to do static analysis and we want really have a practical impact on how enterprise would benefit from static analysis, is that we have to have these specific technical requirements. So the first of all, we have to deliver useful results. So I'm not saying using traditional quality descriptors like soundness or completeness. So I'm saying useful. Okay, so we try to be precise. That we need to understand how program computes, right? They have flow, they have context, and they have path. And usually, my point of view is that we mostly favor under approximation. So we try to achieve precision over soundness, right? So we don't want to report 1,000 bugs to developers and say, okay, so your problem is one of these thousand bugs. We want to just report maybe 5, but these 5 bugs are really worthwhile to look into. Okay. And also we need to be fast, meaning that we can be as fast as the editor feedback, or you click a save, and maybe not longer than a nightly build, because otherwise the next day, maybe programmers still remember what he did, but the next day the programmer would suffer from recovering this memory. And we have to address this coda challenge, meaning that our analysis need to be continuous in time, meaning that it's incremental, have to be incremental, and space being accumulative, because the system is so big. We have to do a distributed analysis. And we have to be open. So O stands for open for customization through APIs or DSLs, so people can define their own source level test cases. And we have to understand dark code, right? So that's what the D stands for. And we have to understand this assembled program dependency through callbacks and distributed computing. So I call it coda challenges. And the horror story is we have to do it all at the same time. All right. So as I said, in my experience, if we don't have any one of these characteristics, we can't get our product to sell. Okay. So that's how harsh the reality is. Or in other words, I think people would not really adopt your analysis technique. Okay. So I said that the static analysis might become irrelevant. So I think I need to speed up a little bit. So what can we learn from the experience? We actually looked into the past. So we looked into, in 2020, we did this analysis of past 15 years, that's starting from 2005. And we looked at all top PL and software engineering conferences. I guess people working in this area knows that these are the venues that are really the top venues, all right? So we looked at how people address these issues, these CODA principles. All right, we'll look at the size of these programs that the paper discusses, and we looked at if they actually discuss how would they deal with the situation, not just presenting a memory leak detector, but does it discuss software being updated all the time, or other aspects? All right, so we looked at this, and the answer is quite disappointing. Right, so you can see that the green boxes are the means that the paper discuss a certain aspect of it, but let me just summarize very quickly. So we looked at around 500 papers, okay, that discuss static analysis. So not all of the papers are about static analysis, but we found over 500 papers, and only 3% of these papers discuss subjects that's over 1 million lines of code. Okay, most of the paper discuss between 10K and 500K. My point of view is that they don't exist in reality. Okay, so any system that you use in real life, it's going to be bigger than this. So so what about code challenges? So fortunately, I'm not really daydreaming. They are there. There are people are actually discuss them, but individually. All right. So only 4% of the papers address two factors at the same time, and no paper address more than two. So this is what I call, these are the strange characteristics, because the academics don't really look into them very, very closely. All right, as close as one might want to be. Okay. All right, so that's our finding, and our answer to this, of course, is not a. So our answer, right, is not a solution to this, but our answer is this Pinpoint holistic value flow analysis technique that that have been described in many publications. Okay, so if you're interested in looking at it, I sort of categorize a little bit. We have paper that discuss the basic capabilities that increase either the performance or the precision of the basic analysis, and we have papers that address the speed or the performance specifically, and we have paper address the the customization of static analysis. Of course, I didn't put the CODA principles here because we're not there yet. We're not there yet. Okay, so so the basic idea of the pointer static analysis framework is to get rid of this layered approach in traditional static analysis. In traditional static analysis, we always start from a pointer analysis, right? So we do a pointer analysis, we build some kind of graph. So either it's a PDG or sparse value flow graph or super graph. All right, so we're gonna start with a pointer, but that's the thing that's going to kill us. All right, so the pointer analysis itself is extremely complicated. Okay, so it's exponential. If you consider context and path, it's clearly exponential, and it's clearly beyond the computation capability of any computer. So our approach is not to do anything about exponent. We want to do something about the base, right? So in other words, we want to adhere to the principles of on-demand, right? So we want to reduce the amount to compute. We have very little solution to the exponent. Okay, so and we'll abandon exhaustive points-to analysis. So it's a quick summary of what Pinpoint, the technical highlights of the Pinpoint platform is that that we first want to do on demand to the bone. So we don't even have a whole program points-to analysis. Our idea is to blend the points-to analysis with the value flow, so that we can have one formula for both the bug finding, the predicate for the bug, and also the predicate for to answer the points to queries, right? So there are no, well, our goal is to get rid of the points to analysis, get rid of the global points to analysis, okay? And there are a few steps. I guess there's a little detailed, but we first do a local purification, computing the side effects, and we try to embed the side effects to the callers. But traditionally, the standardized usually use the clone-based analysis where we embedding the clones up to the caller. But here we don't embed the whole clone. We embed the side effects only to the callers, and then the whole bug finding process would be just a on-demand holistic slicing, right? So starting from where you think there is a null pointer dereference, and you go all the way back to the source, together with the query of answering whether these data flow can go through, right? So that's basically a points to relation, so that we can actually do everything together in a big slice, okay? And also by taking advantage of this program structure, we actually try to filter out lots of these constraints. Because we know the PDG how the PDG look like, we can easily reason if those two paths can conflict to each other, rather than sending it to the SMT solvers, which the SMT has no knowledge about the program structure. So these are the very high level ideas. Of course, the details will be in the paper. All right. So the architecture of Pinpoint is basically LLVM-based. Okay. So we have we work off this LLVM bit code, and we have our own representation. So which is this this is called SEG-UFG. So we have our own intermediate, sort of our own static analysis IR that generated off this LLVM bit code, and then we have separate engines that this IR is important to separate the program representation and also the analysis themselves, right? So in other words, so we could actually analyze different language front ends, and also our backend analysis can be reused to check common code quality issues. Some quick facts that this core engine is completely written from scratch, so we didn't have anything to reference, and we use the LLVM toolchain to allow us to actually do cross-language bugs. We can do, for example, the GNI, go from C, going from Java to C++. Okay, we can check Java directly, and in 2018, we can do 6 CFA, right? So meaning that we can actually reason about 6 levels of call on 40 different bugs for 8 million lines of code in 6 hours. So what's the significance of this is that this is actually what our knowledge of is the first to be able to do this, at least from publication point of view. I don't know if Google has already done this, but they don't tell us. Okay, so all right, so we also have a query language that you can also define your own checker. And we at that time we found many bugs, right? Of course, thousands of bugs in private systems, where the quality is not as high as open source. Okay, and of course, I think I'm almost out of time, but we have made some development recently, well, continuously. So we have tried to increase the speed of performance by pipelining the internal data flow analysis, right? So because traditional parallelization is the old trick for speeding up, but we cannot do this easily for program dependencies because of the shape of the call graph. But we found that if we decompose the internals of the function summary, we actually find there are many parts are independent, and we can actually pipeline them from the caller to the callee. Okay, so due to the time limitation, I will just try to speak of the very high level idea. So recently we have a PLDI paper by applying the same idea to race detection. Okay, so by not doing points 2 separately for detecting cross-thread bugs, we're able to scale in path sensitively to very large systems. Okay, so we will find many will fast because we're on demand, and but we can find we also find 21 new data race bugs in mature open source systems. So let me just quickly summarize. So I gave characteristics of what I call the enterprise scale software, and we want to address the CODA principles, and I think that's missing any of these components, missing any of these part will be will have problems for real use of your technique. Pinpoint is a recent attempt, but still ongoing. We are working on try to make a sort of distributed analysis. We try to make incremental analysis by using persistence, and we actually have already completed a binary lifting to IR, so we can actually analyze binary directly. And we were looking for good people to join us. I think I'm out of time, Jager.
Thank you very much, Charles. I have questions for you, if you don't mind. Well, I start from the beginning. I was making notes. So you said in the beginning that there are certain, like you said, weird characteristics of the software we have right now. Like some of the pieces are dark, the software is above 1 million, and so on. What do you think are the trends now? Where are we going from here? I understand what we have now, but what do you think will happen in 10 years and 20 years with these characteristics? What will happen with the size of the code? What will happen with this dark quality of the code?
I think it's gonna get worse, right? So, well, worse or better for us as a program doing program analysis. I think that especially with the prevalence of AI, that I think the development of Web 2.0 is that even my mom start to use the internet. All right, so which means that our software is like the guy in Microsoft says is eating the world. Okay. So this is gonna get even more serious, especially as the AI trend that push computing into unprecedented level of usage, and so meaning that it's gonna get even prevalent, more sophisticated. More important to get good code quality. Otherwise, it's gonna kill a lot of people, right? So I'm just jokingly say that it's gonna cause even bigger damage if we don't beef up our technique, right? To me, if we don't beef up the static analysis technique, it's just gonna get even more serious, right? So from cybersecurity point of view, it's already a real threat to everything, right? So no doubt, it's gonna get even more serious. Maybe more strange characteristics would emerge.
I agree. Thank you. For the CODA principles, they sound really they sound right to the point to me. But my question is it possible to measure the code compliance with these principles for a static analyzer? Let's say I have a static analyzer. Let's say I develop it and I claim that I pay attention to these CODA principles. So is there some checklist or maybe some criteria which I can go through and confirm and prove that I really is adherent to the principles?
Well, honestly speaking, this is my very subjective view of what we should do. Of course, one can easily tell if, as a designer, if on your conscious mind, if you really address these principles. I don't think it's necessary to quantify these principles. I think, as you see from our field study, that it's very primitive. So people, I don't think they, most of us probably not really bother with addressing a combination of these factors. After all, you get your paper accepted and the students graduate. So there's also very valid reasons for for doing research in that way. But I hope that this is a sort of right now it's a philosophy, or not even philosophy, it's some kind of principle that I hope people will pick up and try to improve on that. But it's not really rigorous, some rigorous definition. It's mostly qualitative arguments.
Okay, thank you. We have one question from YouTube listeners. What do you think about the integration with formal verification? Can formal verification be enterprise scale? I hope you understand the question.
Yeah, of course. So I wouldn't say that formal verification is at a disadvantage based on these components. It's definitely has been proven very successful on smaller scale systems, components, lower level components, and has been very successful. Enterprise formal verification, although it depends on how you define formal verification, and I think the Amazon guys have done something about that. And as far as the sort of the traditional common static analysis tasks, such as finding bugs, answering some queries, I think formal verification still has some way to go.
Okay.
Yeah, for example, taking CODA principles as the criteria. Right, so.
Okay, I have a technical question. You mentioned that you have your own IR on top of LLVM IR, or maybe not on top, but after LLVM IR. So why did you create your own IR? What was missing in the LLVM IR? What did you add, or what did you fix there?
LLVM IR is firstly a IR for doing translation to low-level instructions, and in many ways, it's not really suitable for doing static analysis, where we want to know, we want to build a graph, right? Most differently, an interprocedural graph, right? So LLVM is definitely not really the appropriate representation for that task, right? So it's designed for translation to the machine code. That I think is its primary purpose. And so what we do is that we go from LLVM-IR and we also take elements from the source code to. So another difference is for static analysis, our client is the human, right? So they have to actually look at it and understand what they did. So I think it's obvious to us that we need to have something that's richer than the IR. So, but we take a lot of the nutrients from the IR, as they have done a lot of type resolution, lots of useful. We don't want to do a compilation ourselves, right? So, and it's a good IR to start as a base.
And it seems that every developer, every creator of a new static analyzer has to do something like that, has to invent some layer on top of LLVM-IR, and then maybe the query language, which you mentioned as well, for defining those checkers. Am I right? It's like the work which every maker of a static analyzer has to go through.
Right. So I think the query is a recent trend. That although people have been working on this kind of query system for, as far as I know, for over 20 years, but until recently, I think getting a lot of traction, such as the QL project, right? So, and but for many of this so used to be our clients, they a lot of them also want specialized bug finding tools. So
it's the way to customize the analyzer, right?
So not everyone would desire a high level of degree of customization. So in my experience. But I think that's a trend that's getting significant momentum in recent years, just because it's the other side of the coin, as we have widely adopt software doing things that so complicated, so intimate with what we our daily sophistication of our daily life, right? So human life, and of course this requirement is getting stronger and stronger, right? So whether you want the speed or whether you want the different scenarios to verify or to guard against, it becomes dramatically diversified, and of course customization is becoming increasingly critical for doing static analysis. When we started I think 2017 was 6 years ago, 5 years ago. Most of the I can only speak from the industry in China. This is not a huge demand, right? People want to. They know what the bugs they want to build. They ask us to build it. The bugs want to find. They ask us to build it, and we test it, and they're happy. Okay, so they don't want to have these experts in house that knows how to give specifications. So I would say 5 years ago, I don't see this as a important factor to have as we sell the product, but later on we have increasingly more requests for being able to analyze their own specific kind of problems. Okay,
thank you. One last selfish question from me. Do you have an open source or free version of your analyzer so I can try it myself? Because I'm also working on one analyzer, so I would love to compare and do some benchmarking.
I'm glad. I'm glad you. I actually wanted to include the additional slide. We actually will have a open source version of the system that be able to analyze directly off a binary. So it's very it's easier to use than many other tools that you only need to drop me a binary better with debug symbols. Right, so you just do dash G on your compile system and give us your result, and we're going to analyze this of this binary, and everything else is going to be available. Hopefully, we're working hard on it. Hopefully, the mid-May, we'll have an open source version, and I'll surely let you know.
Okay, thank you. I'll email you definitely because I'm interested.
Okay, great. And give us feedback. Better contribute to
Absolutely.
the project as well.
All right, thank you very much. Thanks for coming. It's really an honor for us to have your talk and hope to see one of your papers in one of our future conferences.
All right, great.
Thank you.
Thank you for inviting. It's an honor from you to speak.